Okay, so we have a example 11.8 here on air conditioning units, and the basic idea is this technician has to go fix 70 of these units, and we know on average it takes 1 hour to fix them with a standard deviation of 1 hour. We also know that it's an exponential distribution, and we want to know how much time should we budget for our technician to go out there. So let me show you a picture of, here's a picture of that actual air conditioning fix times. And what you're seeing here on the bottom is hours, and up here is the number, the proportion that will take at least that much time. So you have a lot of the air conditioners that are fixed with a very simple problem. Maybe someone forgot to plug it in or something else that the technician gets there and it's a very quick fix. So you have a lot of them that can be fixed really easily. And then as you go out here, you have a few that take quite a bit of time. And when we average all of those, that would give us an average of 1. And if we take the standard deviation of this distribution, we'd get 1 also. Notice this is not a normal distribution. So this original population distribution is not normal, but that's fine. We can handle that. What we want information on is when we take a sample of 70 randomly chosen air conditioners, that's what we're going to assume that we have here. Where do we expect the average to be? What do we expect the average time of these 70 units to be, knowing that the original population has a mean of 1 hour and standard deviation of 1 hour in terms of fixing time. So if we budget 1.1, what's the chance that we're actually going to go over budget? What if we budget 1.25? So to get at that, we're going to have to look at a different distribution here. Here's where we're going to look at the distribution of sample means. And to get that, we know that the average of that new distribution, the distribution of sample means, is going to be the same as the population average. That's one of the things we've learned from the central limit theorem. But what about the standard deviation? It turns out it's not the original standard deviation here of 1. We have to apply a correction factor to account for our sample size here. And so if we divide it by square root of the sample size of 70, we see that it's 0.12 of an hour, about an eighth of an hour, which is much smaller than the original standard deviation. So let's take a look at what this normal distribution with a mean of 1 and a standard deviation of 0.12 would actually look like. Okay, so if I plug these numbers into that app, I'm using something just a little more precise than the 0.12 to get the numbers closer to what your textbook has. If you use 0.12 here, that's fine. Main point is, let's ask ourselves what we're looking at here. So this is the distribution of sample means. So in other words, of sample means when our samples are size 70. In other words, of all the different times we could send our technician out to handle 70 different randomly chosen air conditioners, and we look at the average time that it took for those 70 units, plotted them all out, this would be the distribution we have. So our key point here is we want to know what happens if we budget 1.1 hours. In other words, we budget here, it's higher than the average time, but there's still going to be some samples of size 70 that are going to give us an average above 1.1. And specifically, it's this shaded region here, so about 20% of the time it's going to take longer than 1.1. How do we get that if we don't have this handy-dandy app? So what we really are asking is, what's the probability that our sample mean, again, we're sending out this technician for 70 different air conditioners, what's the probability that the average time he or she spends working on those air conditioners is greater than 1.10 hours? So what we're going to do here is, okay, my apologies here. As I was going through, I realized there was a typo in the book, which is unfortunate, but I guess it's important here that you see it corrected. So we're looking for the probability that the sample mean is greater than 1.10. The average of our 70 air-conditioned fixed times is higher than 1.10. And what we're going to do here on both sides of the inequality. So if you remember working with inequalities, you can add, subtract anything you want to either side of the inequality. You can multiply and divide as long as you're doing positive numbers, and none of that will change the direction of this sign. So what we're going to do is subtract 1 from both sides here. So x bar minus 1, 1.10 minus 1, and then we're going to divide both sides by that standard deviation of the sample means, that 0.12. And we're going to do that to both sides. Notice that that is a positive number, so we don't change the direction of our sign here. And why are we doing that? Why are we subtracting 1 here and dividing by this 0.12? Because once we set this up, we're exactly in the format of the z. Here we have our particular average, we have the mean of all the averages, the mean of all the sample means of size 70, we have the standard deviation of all the sample means of samples of size 70. So when we put this together, we have the z-score. So we replace this side. We're doing all of this to replace this with the z. This other side is just calculations. We can do this on the calculator, 1.10 minus 1, and then divide by 0.12 to get this 0.83. So in other words, the probability that our sample mean will be above 1.10 is the same as the probability that a z-score would be greater than 0.83. So what's the probability that a z-score would be greater than 0.83? Well, here's where we look it up on table A. Okay, so again, our z-score is 0.83, so we go 0.83. So that tells us 79.67% of the samples of size 70 will have a mean less than that. That's good for us. That means we budgeted enough time. The flip side of that is if we subtract that number from 1, 0.2033, about 20% of the samples of size 70 will have an average greater than 1.10. In other words, they'll be to the right of that cutoff. Let's take a look at what that looks like. Going back to our applet here, here's that 20% of the time where a sample of size 70 would have an average time greater than the 1.1. In other words, we under budgeted what we really should have. The question then asks for 1.25. If that's what we budget, that's fairly safe. We only have less than 2%. Less than 2% of the samples of size 70 would have an average less than, or greater than this 1.25 hour. So there would still be a couple times where we'd be over budget, but the great majority of the time there we'd be under budget. And to get that, we would set up the exact same problem, except we'd have x bar greater than 1.25 would be right here. Notice that this would not change. We'd still subtract that 1, the average of the distribution of sample means, the average sample mean, and the standard deviation of the sample. That's not going to change. That's going to be the same for any sample of size 70. But this 1.125 would change, 1.10 would change to 1.25. So this number right here is going to be a little higher. This number would be lower. And then this number here would be about 0.018, roughly this value right there.